Well, hello there, and welcome to another unedited episode of the development log that I call The Making of Pokemon Gemini. So if you've watched any of the other episodes, which I suggest you go back and do to catch yourself up, we've been working on a Pokemon fan game that I'm making from scratch called Pokemon Gemini. It's got a whole bunch of, differences and similarities you can compare and contrast when you watch the other videos, especially the first one where I go over the kind of background of the game. But we're going to continue from where we left off. So in the last episode, we added in a player character, which is... where did I put him? In Overworld. There we go. Because he is an Overworld character. So we've got the player. We gave him basic movements. So left, right, up, down. He's aligned to a grid. He moves just like the characters do in Pokemon. You can hold shift to run, so kind of like the running shoes in the actual games where you hold B to run, which makes him move faster. All of the movement is all settled. We even hooked him up to our little region manager here. So our region manager previously, before the last episode, it used to figure out what region the mouse was in, which is kind of stupid because it's not a mouse-controlled game. So we hooked him up so that now it's looking for the player's position and determining the region based on that. So that's all great, but here's the problem. You can move anywhere. You can just walk anywhere. There's no walls, there's no water, there's no ledges, there's no nothing. And so today, we're going to be implementing collision, or at least terrain collision, because there will be other collision later with different sprites, so things like houses and stuff, although we may integrate that with the terrain collision. So, but there will still be stuff like colliding with different trainers and other things that aren't terrain, and that's going to be handled differently. So today we're going to be focusing on terrain and the collisions with terrain. So if you watched the first episode, or maybe the second one, whichever was the one we did the region manager with, you saw how we did the region manager with a tile-based approach. So we paint these tiles in, and then based on which tiles the player crosses over, that determines which region you're in. And the game notices when you've stepped on a tile for a region that's not the one you're currently in, and it switches you over and says, now you're in this region, right? So here's region 0. Here's region 3, I think it was. And we can actually double check that by looking at the tiles. And if we look under region tiles, yeah, so region 0 is red, 1, 2, 3 is purple, so that's region 3. So when you walk from here to there and touch a region 0 tile, it tells you you're in region 0. When you're in region 0 and you step on a red tile, it does nothing, because you're already there. But if you're in region 0 and you step on a purple region 3 tile, it switches you to region 3, right? So we're actually going to be using a very similar approach for collision. And the reason I want to keep using tile-based approaches where appropriate is just because it makes it easier to design levels, right? So things like which region you're in and what tiles you can walk through and stuff like that, it makes it easier to use a tile-based approach where I can just sit here and be like, oh, this is region 0 now? I want to extend region 0? Okay, I'll just draw this out. And now this whole part is part of region 0. So now I've just changed the shape of region 0 without having to do anything with the code, right? Now let's undo that. Oops. That's fine. So in the same way, like as we design, as we design these levels, we're going to want to change the way the terrain is, right? Maybe we'll add a tree over here, or maybe we'll bring a wall down over here. And for all those things, we need the collision to change as well. And so there are a couple of ways we can do this. One is to have the tiles that are actually shown on screen have collision properties of their own. So for instance, let's say there's a tile that's a part of a tree. We could have the tree tile here, and it would look like a tree, and it would also block movement. But I don't actually want to do that. And here's why. There are going to be many different tiles that look different, especially as you get to different areas of the game, but that have the same properties. So you're going to have a lot of tiles that are, that you can't walk through, solid tiles. And those would be like walls, or boulders, or ledges, although ledges are slightly different in Pokemon, and I'll get to that in a minute. Or trees, or maybe icicles, or who knows, what else. But it could be a ton of things that you just can't walk through. So rather than have to code in the properties for each of those things, I'm going to have the actually displayed tiles be totally separate and completely aesthetic. So the ones that are displayed will only be there for the graphics, whereas we're going to create a tile set similar to this region one that will only represent the properties of the tile in terms of collision. And by doing that, we can paint them on top of each other and layer them so that, for instance, let's say, pretend this is not the region tiles, but this is the collision tiles. We could have a collision tile there, and we could put a tree on top of it, and it would look like a tree and block you. But then if we want to change the tree to something like an iceberg, we could just delete the tree, put the iceberg there, and it would still block you because underneath it is this collision tile that says it's solid, right? So that's my rationale for why I want to go with a tile-based approach. I'm also going to go with a tile-based approach for determining terrain types, like water, cave, grass, I guess normal ground. I don't think that really needs one, but water, cave, grass, whatever else I can think of. Because in Pokemon that's important for like what kinds of encounters you can find. I guess shore is one. But that's going to be in a later episode. I don't think we're going to have time for that today. So for now, let's start making the collision tile set, right? So for our region tiles, we figured, what was it, 160? So 10. There are 10 regions, and we figured per room, 10 regions should be enough. That there's never going to be a point where you walk through more than 10 different regions without warping somewhere else, either through one of those gatehouses, or by flying, or by entering a building. Whatever the case may be, there's never going to be a time when you walk through more than 10 regions without going through another warp tile that can put you into a different room with this, so we can reuse these region tiles, right? So what we need to do is think about how many different types of collisions there's going to be, because for a collision tile set, we need to have, a similar setup where we have the tiles already predefined for each type of collision, and then we just reuse them in the actual levels. And it's actually not that hard to figure out. Because the thing about collision with a tile, is that it really only depends on what direction you're walking from, right? So if I have, if I just have a solid object, then all four sides will be blocked off, right? So that's one type of collision. If I have an object you can walk through, I don't even think I need a tile for that, but just to cover all the bases, let's say we have a tile for that, so that's a tile with all the sides that are not solid. So that's two types. Let's say there's something you can walk through from the left but not the right, well, that's another type. So really, we need to figure out how many combinations there are of tiles where each side is either solid or not. And as it turns out, that's actually pretty simple, because what that means is we want to know how many combinations there are of four sides, each with two possible values. So solid or not. And that's just binary. So it's 2 to the 4th, which is 16. So that means we can come in here and create collision tiles. And we will resize this to be 16 pixels tall, because that's the height of our collision, of our tiles. And then it is 16 pixels wide times 16, right? So let me quickly do that here, and now you're getting a little glimpse of stuff that I have open. But 16 times 16 is 256, which I should have known. But anyway, to 56. So there you go. So this right here is our basis for our tiles for collision. Now what's nice about this, I'm going to zoom in a little bit. What's nice about this is you can tell, like if we zoom all the way out, each of our little background grid patterns is 16 pixels by 16 pixels. So that tells us exactly where these lines are, right? So it's actually really going to be easy to do this. But in order to sort of make it clear that these are collision tiles, I do want the tiles to be filled in. And we want to keep them separate. So what I'm going to do, I'm going to make it a little bigger. And then I'm going to fill this in with white. Now, if I were editing this video, I would, of course, have, you know, kind of a speed up right here. But since I'm not, I can't. So I'm doing this every other one white. And since I've zoomed in, these areas are 4 grid spaces by 4 grid spaces. I think I did that one a little too far to the left. So there we go. So 4 grid spaces by, 2 grid spaces by 2 grid spaces, making it a total of 4. I'm trying to get this pixel perfect so that the tiles line up properly. Okay. What I could have done, and maybe what I should have done, but it's a little late for that now, is filled the background with the other tile color and then just layered these these white squares on top of it. But it's a little late for that now. So there we go. And now we'll just fill in the other color. Now I don't want to put black because I'm going to use black to represent the solid sides of each square. So let's pick a different color. Like, say, I don't know, like a light blue? Yeah, that's fine. And now we'll just fill in the other areas real quickly. So that's great. So now, one second. Okay. So now we have to decide which tiles are going to be which, have which side solid. And I think the best way to do this is to go back to what I said before about it basically being binary, right? So, because in the end, what we're going to want to do is take the position of each of these tiles and convert it into some sort of representation so that the computer knows, hey, this left side is solid, but the right side isn't, or whatever, right? And so for that, the easiest way is to use the bits in the index. So basically, just like the region tiles, these are going to be indexed. And before I accidentally fill anything in, let's switch to the tool. So these are going to be indexed with this being 0, this being 1, 2, 3, 4, 5, 6, 7, etc., all the way up to 15. So 0 to 15, right? Now those values are represented by the computer as 8 bits, or actually 4 bits in this case, but it'll be an 8-bit byte and then cut into, we're only using the least significant 4 bits. But anyway, the point is you can use 4 bits to represent each number. So, knowing that, if we use the index of each of these, convert it to binary, and then all the bits that are 1 represent a solid side, we can make sure that our visualization for when we're actually designing the levels matches up to the way the computer is going to see it and interpret it as being a certain side, solid or not. So, for instance, right here, and let's pick black. So right here, actually, you know what? Let's do a line black. Okay. So right here is index 0. 0 in binary is just all zeros, so there are no ones. So we'll just say, we'll leave that alone and say none of the sides are actually solid, right? Now here we have index 1, which in binary is 0, 0, 0, 1, right? So now we have to determine which sides represent which bits, and it should be really simple to do that. We just pick any one. Let's say we'll start with the top as being the first bit, so the bit all the way to the right, and then we just go clockwise. So bit 1, 2, 3, and 4. So for the number 1, the only bit that is 1 is the last bit, so the bit 1. So we can set side 1 to solid, right? And I did go a little too far on that, but that's not a big deal. We can just overwrite that like that. Nope, like that. There we go. So there we go. So now we have the first tile done. So index 2 in binary is 0, 0, 1, 0. So the first bit is 0, so we're not going to fill the top in. But the second bit is a 1, so that's this side since we're going clockwise. So we fill that in. Done. This is 3, which is 0, 0, 1, 1. So in that case, both the first bit and the side bit are set. So there you go. Here's 4, which is 0, 1, 0, 0. So neither of these two, but the third bit is set. So we'll fill that in. So now we've got 5, which is 4 plus 1. So that's 0, 1. 0, 1, 0, 1. So that's the top and the bottom, right? 6 is 4 and 2, so 0, 1, 1, 0. So 0 on top. Okay. Is this on the right side? Yeah. 1, 1, and then 0 across the left side. 7 is 0, 1, 1, 1, right? 4 plus 2 plus 1. So that's 0 on top, but then all the other sides set. So 1, 1, and then 1 here. 8 is 1, 0, 0, 0. Wait. Shoot. I'm doing this wrong. Oh. This is why it helps to write things down. So this one is actually not that last bit, but yes to the top, because it is 0 is this one, and it's 1, 1, 1, 1, 1, right? Because we're going from right to left. So 1, 1, 1. So let's make sure I got the other one right. So this was 0, 1, 2, 3, 4, 5, 6. So that's 2 and 4, which is 0, 1, 1, 0, 1, 1, 0. So that's fine. Here's 5, which is 4 and 1. So it's 0, 1, 0, 1. 0, 1, 0, 1. So that works. Here's 4, which is just the bottom, all right? 0, 1, 0, 0. 3 is 0, 0, 1, 1. Yeah, okay. So all the others are right. So now what were we up to? Now that I got that settled, we're up to 0, 1, 2, 3, 4, 5, 6, 7. So now we're up to 8. And 8 is just 1 and then the rest zeros. So that's just this one. 9 is 8 and 1. So that's 8 and 1. Right. 10 is 8 and 2. Nope, too far over. 8 and 2. 11 is 8, 2, and 1. So that's 8, 2. That's a little too far over, but that's fine. Sorry. You know what? 8, 1 and 2. There you go. 12 is 8 and 4. So 8 and 4. 13 is 8, 4, and 1. So that's 8, 4, and 1, right? 14 is 8, 4, and 2. 10, 11, 12, 13, 14. Yep. So that's 8, 4, and 2. And then 15 is all of them. So 8, 4, nope. 8, 4, 2, and 1. So if we look at this, each of these tiles should be unique. So nothing and full, those are unique. One on top. If we look at just the ones that have one on top, one on the right, one on the left. I think that works. I think that works. It'll be a lot easier to see once we break it down into a tile set. So 16 by 16 tiles, and we have our collision tiles. So if we come into here, and we click on our tiles, let's make a new layer. So our region tiles are on layer, what is that, 1 million was the default? 2, 3? Yeah, 1 million. So let's put our collision tiles one layer above that. So 999,999. So they're one layer above that. And we will pick our collision tiles. And let's start creating our collisions. So we know that in this case, the region should have a solid border. So that's the last one. So if we look at this without our grid, we can see that we are using the solid border. So in this case, I'm actually like putting solid barriers over where the region tiles are. So I'll never be able to step on these region tiles, but that's okay because we're not leaving the region that way, right? We're only going to leave the region this way. So this is where the region tiles really need to be. And so if we do this as a solid border, that's fine. So now as we move back and forth, we can switch regions here, but we shouldn't be able to move outside of there. Now that code to detect the collisions hasn't been created yet. We're going to do that in a second. I just want to make sure that these tiles are correct. So we can see over here is an upper tile. So if we link that, then you can't move from above, right? Over here, let's see, is a corner tile, just for those corners, for the top and right corner. So yeah, I think all of the options are represented here, and because we used that binary system, now when we go to code for the collision detection based on these tiles, it'll automatically be able to sort of interpret those tiles using the binary form of the index to come up with, to decide whether one side is solid or not. And so what we're going to do is we're going to test it first without the player, without any collision, just to see, well, actually, no, you know what? Let's go directly into the player, right? So in our movement code, right, we literally just, here we have, okay, so here's where we do the actual movement. So let's put a little comment here, actual movement. I don't know what we want to call it because the movement itself is done down here. This is what actually sets your goal. So actual movement goal setting, right? And so what I want to do is create a little script to decide whether something is a valid goal. So whether you can move this way. And the reason I want to create a script is because other things that are not trainers are also going to need to determine whether they can move through things. And it'll just clean up the code a lot to have a reusable function for it. So a script. So we'll call it if can collide, or sorry, if can move through, right? Because we want to know if you can move through, then set it. So if can move through, and then we want to have the position. So we're seeing about the tile at go to x minus 16, right? So go to x minus 16 without a change in the y. If you can move through that coming from the left. So to determine left, right, and all of that, I think what we should do is create some constants. So I was going to use vk left and vk right, but since we're going to be interpreting this based on the binary representation of the index, the easiest way to determine whether something is solid or not is to pass in a bit mask. That is a value where the only bit that is 1 is the direction you're trying to move through, the side you're trying to move through. And then you can just compare that to the actual bits of the index of the collision mask, the collision tile, and then you can figure out whether it's solid. So when I start implementing this, it might be a little clearer, because I know I'm not explaining this in quite a clear enough way. So the first thing we want to do is come in here and create some constants. So constants, oh no, wait, no, these are not, sorry, they're called a macro, or they're macros technically. So all configurations, let's create a constant. So these are some constants that already exist for various uses with other stuff, mostly dialogue system and determining which version of the game you're in. But we're going to add a new one, and we'll call this mask left. Or let's make this easy. Let's go in order. So up, the top, or I guess let's call this mask top. Nope. So the top, we said, was going to be the last bit. So that's just a value of 1, because only the last bit set is 1, right? Then you have mask right, which we said was the right side. And we said that was going to be the second bit, so 2. Then we have mask bottom, which is the third bit, which is 4. And then we have mask left, which is the fourth bit, which is 8, right? So 1, 2, 4, and 8 are the 4 values that represent just those bits set based on how we created that collision tiles image, right? So now what we can do is we can see if your x is minus 16, we want to check the right-hand side to see if it's solid, because we're moving to the left, which means we're coming from the right and moving left, right? So mask right, and I think it's actually easier because we're saying that 1 is solid to say if not side solid, that, then go to x. So we're going to create the side solid function, which is why it's giving me this error here, because we haven't created it yet. It doesn't know what that means. But we're going to create that in just a second. But first, we're going to copy this over to the other 4 directions. So, yikes. What I should have done is copied just this without the indentation. And so now we can say, in this case, it's x plus 16 is the tile we're moving on to, or trying to move on to. And so since we're moving to the right, we're moving from the left, so we're taking the left mask. In this case, the x is staying the same, but the y is moving up, so y minus 16. And since we're moving up, we want to check if the bottom is solid. And likewise, for when we move down, we're doing y plus 16, and we're checking if the top is solid, right? So there we go. So now all of these we'll check to see if the side is not solid before moving. And it's doing that by running this function, this script, side solid, which takes the position of the actual position you're trying to move to, and then the mask that we're going to compare to the index of the collision tile at that position to see if that side is solid. So good. So now we need to create that function here, and I'm going to create an overworld script, or an overworld group of scripts. We're going to create a script in here called side solid, and then just for good documentation practices, we're going to include a syntax here. So it's side solid x, y, side mask, right? And so because I've used this triple comment thing here, so normally comments are double slashes, or multi-line comments are slash and star, but with the triple slash here being the first line, GameMaker is going to automatically know that that is a documentation, so that if we look in here, so if we start typing like side solid, then you can see immediately at the bottom here, it gives us x, y, and side mask. So we know what the parameters are for that script, which is great. So the good documentation practice when you're using GameMaker is to include this at the top. I think it was introduced in GameMaker Studio only, so previous versions of GameMaker won't be able to do that automatically for you, but GameMaker Studio and above, this is a really nice documentation practice to get into. So yeah, so we have our side solid function, but it doesn't do anything. So the first thing we want to do is we want to set xpos, or yeah, let's call it xpos. I was going to call it xx, which is kind of my habit, because x and y are built-in variables in GameMaker, so you can't use them. But I think xpos is a little clearer. So xpos is argument 0, ypos is argument 1, mask is argument 2. So we just pulled all of the parameters in, and now we need to work with them. So the first thing we need to do is get the tile on the collision tiles layer at the given position, right? So if we do tile find, is that not the method? Oh, tile layer find is the method. Sorry, it's not a method, it's a function technically. Minor difference. Anyway, and the depth that we put that at, the collision tiles were on layer 999999 because they were one less than a million. And the x we know, and the y we know. So this will give us a tile. So now we can get the tile x, which is, so remember, the index that we're using here is not actually an index so much as the x position, right? So this is at 0, 1, 2, 3, etc. But it's actually at x position 0, 16, 32, whatever. You just divide by 32 and you get that index. So it's the x position. So we'll do tile get x. No. Shoot. What was it? Tile background get x. Oh, man. Let's see. I have forgotten. Left. That's what it is. Right? Let me just check the documentation. It's always good to check the documentation when you're unsure, because one of those functions, tile get x and tile get left, one of them is the position in the room, and the other is the position in the background. Now we want the position in the background, not the room. So let me just make sure I'm using the right one. Tile get left within the background image. So see right here it says within the background image asset of the tile. So that is what we want. So tile get left of our tile. So now we have this tile x, and now we just tx divided by equals, or we'll just use tx equals tx div 32. Now the reason I'm using div instead of divided by is because div will always round the result towards 0. So in a case of a positive result, which it should be, it'll always round down. Now technically, if I created this image correctly, which I think I did, each of these tiles should be exactly 16 pixels apart. So dividing by 16, oh, not 32, 16. Dividing by 16 should always give you an integer anyway. But just in case I screwed up the positioning on something, I'm going to set it to integer division instead, so that it'll round down and it'll be, basically close enough so that it'll still work. I shouldn't have to, but just in case. So that'll give us our index, right? So now all we have to do is return whether this index bitwise ANDed with the mask is greater than 0. That's it. So what does this mean? So in programming, two ands is a logical and, which means this side is true and this side is true. One and is a bitwise and. What that means is take all of the bits in here and all of the bits in here, and where where the same bit in both values is equal to 1, the output bit is 1. Everywhere else the output is 0. So since our mask values all have only 1 bit set, what this is saying is basically if that bit is also set in this index from our tile, then the value will be something more than 0. Specifically, it'll equal the mask in this case, which will be 1, 2, 4, or 8, right? But if that bit is not set in this index, then the result will be all zeros, so it'll be equal to 0, which is not greater than 0, and so it'll be 0. So by doing this, we're saying true or false based on, true if that side is solid, false otherwise, right? Because that bit will be set to 1 if that side is solid, which then ANDed with the mask will be greater than 0. So that's why I wanted to do it the bitwise way, the binary representation way, because it makes it easy to do something like this, right? I mean, all of this is not even math, or really even coding. All of this part is just getting the values. Once you have the values, this is to convert it to an index, one little operation, a division, and then this tiny little piece of code determines whether it's solid. So by doing it the binary way, it definitely makes it a lot easier. So if I've done everything correctly, because we have our, nope, wrong room. Because we've already put our collision tiles in there, and these tiles should have index 15, which is all 1s, which means no matter which side we try to move from, the value will always be 1, and so you'll always get a value greater than 0, and it'll say it's solid. This should mean we can't move around the edge. Now, what I was doing for the regions, when it's created, nope, not that one. Yeah. Where did I actually, oh, when the room starts, we hide layer 1,000,000, which hides the region tiles. For now, just during our testing, we are not going to hide the collision tiles, just so we can see where they are and make sure everything lines up. Once we confirm that everything's working, then we'll go in and add a little bit of code, just one extra line, to hide those collision tiles so that they're not visible to the player. Okay, so we can, see, immediately we get a bug. And the problem is, the tile does not exist, tile get left tile. Aha! Edge cases. And in this case, it's actually going to be the more common case. So what we failed to do we find the tile at the position you're moving to, right? And then we try to get where it is in the background, so the x coordinate of it, right? But what happens if you're not walking onto a collision tile, right? We do have that collision tile here that is all not solid we can use, so we could just fill the whole background in, the whole room with those tiles, but that's wasteful. So a better way is just to check if the tile even exists. So if tile exists, tile, if the tile does not exist, I should say, then we just return false. Because if there is no tile there, then when you check if the side is solid, the answer is no. It's never solid because there's no collision tile, which just by default means that you can walk through it, right? So yeah, so this should fix that bug and it should now not crash. So always remember when you're coding edge cases, right? Because in a case like this, it's not even an edge case. It's just, hey, I just assumed that you'd always be walking onto a tile, but of course most of the time you're not going to be, so it broke. But now, there we go, we can move again without crashing, and I can't move through this. And if I hold the button down, the animation still plays, which is actually nice. I kind of like that. I don't think it does that in Pokemon, but I kind of like it. Oh, but then when you do this, it stops playing. So we are going to want to stop the animation at that point too. But we cannot move up or down or left or right through these. But the region detection still works because we still have that strip of region there. So that is really cool. So now we can try one-way tiles, but first I want to fix that animation. So the animation, if the animation is playing when you hit a wall, it continues playing. And the reason for that is because we have this here, right? So what this is doing is, like, if you're pressing a key, it's going to go into one of these and never get here. So it's never going to stop the animation. So instead of having these nested if statements, I should be putting these into a logical AND. And then get rid of those empty ifs. Right? And so by doing this, it'll, if the side is solid and it can't move, it'll then not go into this at all, and so it'll get to this else, and it'll stop the animation. And so I just need to do that for each of the different directions. So let's move that one for, nope, leave the actual movement. Move that back. Now we have for moving to the right. Move that. And then the last thing is for moving to the left. So we put that up here. So I wanted to fix that now because I did just notice it, and it is, as you can see, a pretty easy fix. So if we save and run the game, you should see that if I start the animation by walking and then I walk into a wall and I don't let go of the key, it should still stop the animation when I hit the wall. There you go. So I'm holding the button, and as soon as I hit the wall, the animation stops because you can't move anymore. So that's fine. Now, one thing that you can do in Pokemon games is you can change the direction you're facing, even if you can't move in that direction. And I think that needs to happen because checking for what you're interacting with, you want to be able to interact with things even if you can't move into them. So that is something that this needs to add. So when we change the sprite, right, it happens here during the movement. So I think instead, well, maybe not instead, but in addition to that, we should also, See, we wanted to change the direction that you're facing when you press the key, even if you can't move there. But here, this code's only going to run if you can move there. Now, before we had it in a nested if statement, which would allow us to add the code for the sprite separate. But then we saw that the animation would continue playing. So to capture both of these, I think... What's the best way to do this? I could do it with a bunch of extra checks for what key you're pressing. I don't really want to do that because that seems there's a lot of code duplication, and there's a concept in programming called DRY, D-R-Y, which stands for don't repeat yourself, because you should try to reduce code repetition as much as possible, otherwise it gets inefficient. So what is the best way to do this in a dry fashion? Well, I believe that GameMaker does have an option for short circuiting, and I'll explain that in a second if I can find it, if it's here. Short circuiting. I don't see it. Maybe scripts and code. I want to say it automatically does short circuiting. There was an older version that gave you the option to turn it off. I mean, we could always just test it, but I want to be sure if I can. Short circuit, yeah. It is under the general global game settings. Oh, it's in the global game settings, that's why. It's not in the editor, or the IDE settings. Short circuit, okay. So short circuit is on by default. Good. So what short circuiting means is that it's going to run this. We have this AND here, right? So it's going to run this and check if this and this are both true. But the thing is, if this is false, it doesn't have to check this at all, right? Because if this is false, then we know they're not both true, and it can just move on. And so short circuiting is when it does just that. If it sees this is false, it's not even going to run this side of the code. It's not going to do it at all because it doesn't need to. And so we can use that to our advantage. We can do something like this. Sprite index equals... Oh, but that's gonna... Okay, this may or may not work. So I'm going to try it first. Sprite index equals, and what's the sprite? Sprite player. Spur player left. There. So basically, again, assuming this works, what it's going to do is if you're pressing the left key, then it's going to check this because that's true. So to see if both of them are true, it has to check this. So in order to check this, it has to run this, and that is going to execute this assignment, which is going to set the sprite index to sprite player left, which is what we want. So if you're pressing the left key, it'll automatically do sprite player left. And that's going to actually return the value of sprite player left, because that's how assignments work. At least that's how they work in other languages. I believe that's also how it works in GameMaker. And then, because that is a non-zero value, it is going to count it as being being true. And so then if these two are true, then the other AND here says this needs to be true as well, so it'll run this anyway. So what it's going to do is just going to insert that assignment in there so that if you're pressing the key, it'll automatically run the assignment no matter what. And this is actually a common technique in JavaScript. When people use JavaScript, they use short-circuiting like this to run code on certain conditions in a kind of compressed manner all the time. I don't know if it's considered quote-unquote good coding practice, but it works. It does everything that you expect it to. It's consistent, and people do it all the time. So I'm going to do it for this. So we're going to include up, and we're going to include down for the down key. So the only thing I'm worried about here is if you're holding the key down, then every tick it's going to run this, and I think it's going to reset the sprite index, which means the animation is going to stop. Maybe. But let's see if you change direction at least. And then we can figure out how to fix the animation issue later. So moving up is the only thing that works. Well, that's interesting. Overworld, characters, trainers. Sprite player up is the only one that works. Huh. So I just broke the movement. What if I do that greater than 0? What if I say greater than or equal to 0? Because I think there might be some issue with it not evaluating to true. So if we say that, all resource IDs start at 0 and go up from there. So if it does return the assignment value, or in this case, the sprite, the way I think it does, this should still work. So I'm not quite sure why it's not, but hopefully putting this check in there fixes things. So I can move up. I can't. Oh, that's interesting. I can move left and right. Oh, but now I can't move up and down. I just moved up, but now I can't. Oh, that's so weird. Okay, so this short circuit approach, which is a little hacky, is not working. So we have to come up with a different solution here. Surprise, surprise, using a potentially hacky workaround doesn't work. So let's see. What's another good way to do this? I'm trying to think of a way to do this in the most, or the least repetitive way possible. So we're not changing the go to X and go to Y. You know, I don't think we can do this without repeating ourselves somewhere. I don't think there's a way. Either we move these solid checks into a nested conditional, at which point we'll have to copy the animation stopping code, these two lines, in each of these. So we're going to have to repeat it 5 times total. Or we put in 4 extra checks for the keyboard and copy those, and then set the sprite according to that. And so I guess repeating ourselves 4 times is better than repeating ourselves 5 times. So yeah, I guess we'll just put in the extra checks. So we'll put in the checks before here, because that way when this runs, it'll still set the animation speed. It'll still stop the animation speed when you hit something. So sprite setting. But what we can do though is once we put the code in here to set the sprites, we can get rid of it from here. We can get rid of it from here and just have these disappear and have the sprites only set up here. So it reduces a little bit of the repetition, I guess. So if keyboard check VK left sprite index equals, was it spur player left? Yeah. Else, and you know what, let's make this easily readable. Clean code. So it was left, then right. We want to make sure that these checks are in the same order as this, so that the movement is prioritized, and sorry, that the sprite is prioritized in the same way as the movement, so they match up. So right, and then it was up and down, right? Yeah. And actually what we can do where do I, oh, the image speed is set there. Yeah. Yeah, that's fine. So now this will be changed to down. This will be changed to up, up. Okay, and so now we can get rid of this because we're setting the sprite when you press the key and not when you do, not when you're actually moving. So now, again, the only issue is if it runs every tick or every step, then if you hold down the key, it might stop the animation from running because it'll keep resetting the sprite, and we can fix that pretty easily with this code. But let's see if the movement works too. Oh no, the animation works just fine. Good, cool. So now the key question is, yes. Oh, sorry, lost my mic for a sec. All right, so now even though we're stuck in a corner and we can't move, we can still rotate, which is exactly what I was looking for. So we can sit here in the corner, and that's all great and fine and dandy. Now in the original Pokemon games, even if you could move somewhere, if you tap the key, it would you would rotate without moving. I don't think that's a necessary thing in this game. As long as you can turn to face objects, it doesn't matter. So that is fine and dandy. Oh no, nope, that's fine. Perfect. So we have collision now. Now we just have to test to make sure that our collision code handles one-way collision as well, which it should, but should is never guaranteed in, we'll hide those. Should is never guaranteed in programming. So this one is just solid from the top. So let's put that there. So if you look, it's only solid from the top according to the tile, which should mean if I run the code, I can move up through it and through the sides and all of that, but if I try to move from the top, I'll hit a wall. So let's check that. I can, in fact, move up through it. I can move through the left and right, but if I move down, I stop. Good, it worked. I hit a wall. That is exactly what we wanted. So that's great. So how much time do we have? We've been going for an hour. I believe that is the end of this episode. I was about to implement ledge jumping. So basically, if I were to try and move through here, because I can't move this way, but I can move up, technically this would probably count as a ledge in Pokemon where you can jump one way but not climb up the other way. And there's an animation for that. And I was going to implement that animation, but again, this has been going on for an hour, which is longer than I expected. But there we go. We have collision of terrain. We can now pile up terrain collision. So before I leave and end this video, I do want to add one little thing. And I'm going to put this in the region manager only because tile hiding is already in there, and that's all this event does. So we're going to hide layer 999999. So now, when we run the game, we should see absolutely nothing, but we should still bump into walls. They're just invisible walls, which, by the way, using a system like this where the images are separated from the tiles that are used for collision also means we can do invisible walls super easily. So we walk, we hit a wall, we hit a wall. I don't remember exactly where I think this is where that other one way, yeah. So we walk sideways through it, we go up through it, but we hit a wall. So there we go. Done for the day. Next episode, we're going to add that ledge jumping animation, and I think we're also going to start working on another tile-based approach for terrain types. So water, grass, caves, buildings, whatever else I said, plus whatever else I can think of that Pokemon uses. So until next time, keep colliding, not too hard.